So today we're going to come back to the compact fluorescent lamp. Before we saw that it had a rectified front end, full wave rectified, and we'll see some of the effects of that. But this time we want to look at the resonant output converter. And I started off by measuring the voltage across the tube and the capacitor that's in the middle of the two tube filaments. You could look up the circuit online if you liked. To measure the voltage, I'm using my differential probe that gives me isolated voltage measurements again. If you haven't got one of these, don't do any of this at home. It's the mains voltage is very dangerous. But this allows us to do the experiment. Now, it's a resonant circuit, and resonance, as you might know, is like ringing a bell. And the circuit, the compact fluorescent lamp, needs to get into the mode where it's running nicely, producing light. That's the whole point. But we have to fire the thing, or trigger the arc inside the fluorescent tube part here. And that takes a little bit of voltage. So I can show you that. I've put my probes inside there across. Let me just check it's clear. We look ready to go. I've got the oscilloscope primed and ready to go. So we simply turn on, and there we have it. And you can see several features now coming to the lamp lit very quickly. We can see several features in the trace here. I'll just block out that light so you can see the scope a little bit more. So you see the resonance build up very nicely. We get up to this point here. That's a very lovely resonance with very nice sine waves coming in there. Then, interestingly, it collapses down to this lower level. Well, what's happened there? Well, that's when the arc is initiated inside the tube. Now that the arc is initiated, we get the light. So we can measure that and just see how long that took. It's on 25 microseconds a division. It's taken about 4 divisions or so, 5 divisions. So that's just over 100 microseconds to strike the arc. So we're producing light very quickly. We can also see that there's quite a high voltage across the tube at that point, and we need that high voltage to break down the gas inside the tube. Once we're running, you can see the waveform takes on quite a different form. Now that's very interesting too, because in the circuit this is an LC resonance. But once the arc has lit, we have now shorted out a small capacitor with the arc. The arc is in parallel with that capacitor. So now we have a much bigger capacitor in series with our inductor in the resonance circuit, and its natural frequency is much lower. But notice that this basic frequency here is very similar to the basic frequency there. So in fact we are switching at about the same sort of frequency, but we're now running above resonance. So we can go and look at that in a bit more detail. If I just now run the thing, the lamp is running, so I'll change the trigger. So we'll set the trigger to normal. There we go. And there's, in fact, a low current. Now the arc is lit. We have a low voltage across the system. A pretty nice waveform there. I can just tidy that up a little bit maybe. There we go, something like that. So that's very characteristic of switching at above resonance. There's a natural frequency in there which is much lower, but as soon as it gets going, we switch it. And then it gets going in the other direction, we switch it. So we're switching faster than the resonance, and you get this very characteristic triangular type of waveform coming out. So it's a very neat way of making this circuit. It's a very impressive circuit. What we haven't seen so far is the switching. We're just looking there at the arc, and in fact that will be approximately the current, because the arc is resistive at this point. So we're basically looking at the current through the resonance circuit there, which is very nice. Now let's go and change that. Let me turn it off and unplug. Now we're going to look at the voltage actually applied to the resonant tank circuit. So I've prearranged these with wires. So one of them is black because that's what I've called zero. It's not ground. it's the zero on the supply produced by the rectifying diodes. You can go look at my other video for that. There's the smoothing capacitor, rectifying bridge there. So I've got my zero at the bottom of the smoothing capacitor. This is the output of the switching transistors. There's two switching transistors. We can see one there, rather small, and another one buried in there. And we're just looking at the midpoint of those two, and hopefully that will turn on. Like that. And bring the scope back on. And there's a nice waveform for the switching. Let's look where ground is. So it's switching from just 0 to positive, gentle edges there, and there's our frequency, the same frequency as before. Okay, some interesting things to notice here. Why is this wiggling around at the top there? Well, that's our smoothing. So if we go back and see, as we just changed the time base, and then we change the trigger, there we go. So we can see that our peak voltage is changing. Well, if we put that on line, so we're now triggered from the line, there's our smoothing, our capacitor smoothing that we saw last time. And within that smoothing, we have this high frequency switching. So that's our DC link is varying for our high frequency inverter. Well, let's go back to our inverter waveforms. So we need to change the trigger now. There we go. So that explains that wiggling top there. Let's just crank out that time base a little bit. There we go. Very interesting, very defined smooth edges there. There's our ground there. So that's 0, that's off. So that's the lower transistor in the inverter on. This is the upper transistor in the inverter on. Why are these edges so gentle there? Well, because we've run in above resonant mode, we can put a small snubber on the transistors, on the midpoint in fact. So when we switch the transistors, the current transfers to the snubber. It's more or less in that interval, it's a pretty constant current, so that snubber capacitor moves that center point voltage almost linearly through there, and you can see that, crank it out. Very smooth, almost linear through there on both edges. So that's explaining a snubber action. Now, why do we want to do a snubber? Well, we want to make the switching efficient. This is going at approximately, this is 10 microseconds of division, so that's it's going at approximately 40 kilohertz or something like that, 20 microseconds per cycle, so that's, I guess, 50 kilohertz. Let's move it a little bit. It's about 50 kilohertz, this tube. Is it? 3 cycles, 30 microseconds, 33 kilohertz we're running at here. So that's a high switching frequency. There could be a lot of losses in our transistors because of switching. Well, we've added a snubber, so there's virtually no switching loss at all. What does that add up to? Well, we now have a circuit that's very efficient. There's very little heat coming out of the electronics. Almost all the heat is coming out of the tube there with its resistive characteristics. So there we have it. The compact fluorescent lamp, resonant circuit, running very cleanly at resonance to start, and then once the arc is lit, the frequency changes of the resonance, the switching stays about the same, and we go into operation above resonance, where we can have very loss-free switching operation. So there's a lot of lessons to be learned there about how a compact fluorescent lamp works and how power electronics works. Thank you.